Howdy, and welcome to Lesson 1 of Calculus, where what we talk about is calculus, rate of change, the idea of the tangent, and consequently the need for limits. So first of all, what is calculus, right? So calculus is basically a study or a means to model rate of change. And a good example of rate of change, and the one that we're going to use in this lesson, is the speed of a vehicle. A vehicle that's traveling down the road, for example, has a certain speed, which is to say that its position is changing as a function of time at a certain rate. The rate of change of the position of the vehicle with time is its speed, and calculus allows us to study that, and more importantly, from a practical point of view, to be able to model it. And literally every physical phenomena in nature involves some sort of rate of change. And so calculus is an extremely important mathematical study and on a practical level, a mathematical tool that allows us to understand, model, and in the ultimate goal, predict the rate of change of a certain physical phenomenon. So calculus and rate of change in some respects are synonymous with each other. When we speak of calculus, we're really speaking about the rate of change or the change of something. And the way that we fundamentally determine that rate of change is using a concept called the tangent, which you probably would have learned about in your geometry class, and we'll talk about that today. But what we'll also talk about today is we'll learn that the tangent by itself isn't easily defined or described or determined unless we introduce the idea of limits. And so invariably, when you start studying calculus, the first idea that you really learn about and begin to develop a tool for is the idea of limits. And this is essential because it helps us to determine the tangent, and the tangent is what we use to determine the rate of change. Okay, and so that's the connection among these four different words: calculus, rate of change, tangent, and the need for limits. Okay, so like I said, in order for us to really understand rate of change, what we're first going to focus on is the speed of vehicle. Okay, and so let's suppose that the speed of a vehicle, an automobile, for example, is described on an xt plane, where x is the position of the vehicle, and t, of course, is time. Okay? And so if we were to draw what x looks like as a function of time, t, for a vehicle that's traveling at a constant speed, then that curve would look something like the following, for example. Okay? In other words, it's a straight line, or it would be represented by a linear equation, a first-order equation. And anywhere along this line, since the speed is constant, the vehicle's position, change in position of the vehicle, is the same. That change in the vehicle's position is the same at any moment in time, which is to say that its speed is constant, right? And so we can summarize this by saying that since the vehicle's speed is constant, its change in position with time is also constant. So we consequently see a linear relationship between position and time. Okay? So it's very easy for us to look at this curve and say, okay, well, the rate of change of position is the same everywhere. And if I want to determine that rate of change in position, I simply take the slope of this curve, right? So this essentially becomes m, where m is the change in position x with respect to time, okay? And anywhere along this curve, m is constant, right? It's a first order linear equation. But what if the speed of the vehicle, or to be more precise, what if the position of the vehicle if the speed of the vehicle, if the position of the vehicle x is a function of time, the rate of change of that position of the vehicle is varying with time, we might get a curve that looks something like this, where we have accelerations and decelerations and accelerations and decelerations, but ultimately the vehicle is moving forward with some position x as a function of time, okay? Okay, so now real quick, before we get too far into really fully scrutinizing and analyzing this curve, it's important to note that, you know, when the vehicle starts at its initial destination, right, which I'll say is time t equals 0 or t naught, to the time that it gets to its final destination, which we might call, for example, t equals t final, okay, I can certainly draw a straight line between these 2 points, and I can take the slope of that curve and I can determine the rate of change of the vehicle as it goes from its final position relative to its initial position and calculate the time it took to do that and correspondingly determine what we would call the average speed, okay? So this slope m that you see here would be the average speed of the vehicle as it travels from its initial point to its final point, okay? But we may not necessarily be concerned only with the average speed of the vehicle. We may instead be concerned with the instantaneous speed of the vehicle at any given moment. That's where we now have to employ the idea of the tangent, okay? So if we kind of clean up our drawing here a bit, and let me go ahead and redraw our curve. It might not look exactly what I had before, but you get the idea, okay? So if we wanted to determine, say, the instantaneous velocity or the instantaneous speed of the vehicle at any given moment in time, let's suppose we pick this point right here, okay? We know, based on this earlier description, that we have to calculate the slope of the line right at that point, okay? This moment in time, which, again, we'll just refer to this as, say, for example, t1, okay? Well, how do you calculate the slope of this line at that singular moment, right? The way that we can do it is by imposing at that point the tangent line t, which we'll refer to also as t, not to be confused with time t, but rather the tangent t. And then we can go ahead and have that tangent line just touch our curve at that singular point, at that one point. And then we can go ahead and calculate the slope of that line. And the slope of this line then becomes the instantaneous speed, right? So m sub t, which is the slope of the tangent at point point t, which also happens to be the instantaneous speed of the vehicle at time t. Okay, so conceptually, we understand that, right? If we want to determine the instantaneous speed of the vehicle at this point, t1, we have to determine the rate of change of the vehicle at that moment, which requires us to know what the slope of the vehicle's position as a function of time is at that moment, which, without drawing a tangent line at that point that matches the slope of the curve at that point, we really can't do. And so it's necessary for us to draw the tangent line at that point and then determine the slope of the tangent line, this m sub t, which then corresponds to the slope of the vehicle's position x as a function of t slope, corresponds to the slope of the vehicle's curve at that moment in time, which then thereby allows us to instantaneously determine the speed of the vehicle at that point t1, okay? Okay, so now let's just reflect for a moment, because the way that I drew this tangent line, it sort of looks like that line is in fact tangent to the curve at point t1. But how do I necessarily know that that line is exactly tangent to the curve at point t1? Well, let me draw some other curves to sort of highlight what is meant by that, okay? And to do that, what we'll first do is we'll define the concept of the tangent, right? And so basically, one way to think about the tangent is that it's an imaginary first-order line that just touches the line of interest. And so, for example, the line of interest in our example is the x is equal to a function of time, right? So basically this curve that you see here, that's our line of interest, okay? And so you can see that what we've done is we've drawn a tangent, this line t, right, which is just touching the line of interest at the point that we're interested in having that tangent occur, okay? So let's kind of dissect this definition a little bit more and visualize it one way, but then identify some problems with the way that we have the tangent defined and the way that we visualize it, and then bring in the concept of the limit to be able to help us exactly determine the tangent at the point of interest, okay? So to do this, it's very often instructive to rely on the circle, right? Because it's very easy to draw a tangent to a circle, right? Basically, since the perimeter of the circle, if you will, the outer line of the circle is always changing as you go around the circle, it's rather easy to simply say that, okay, this line that I've drawn right here is tangent to the circle exactly at that point, right? And if I were to take my infinitely powerful microscope and zoom in further and further and further on this circle, I would get so close to that intersection between the tangent and the circle that I'd be able to confirm that the tangent is touching the circle once and only once, right? At an infinitesimally small point on that circle, the tangent is touching the circle, right? And that's the way that Euclid thought about the tangent, right? Basically, Euclid described the tangent as a line that intersects the circle once and only once. And that's sort of that idea of, if I could infinitesimally zoom in on the circle, you would see that the tangent literally touches the circle at one infinitesimally small point, okay? Okay, well, this idea, this concept, and this visualization works really well for a circle, But what about our case, where we don't have a circle? Right? So let me return to our drawing that we have up here. And let me draw two situations where we can scribe a tangent that touches once and only once. So this curve here touches x as a function of time once and only once, right? If I were to infinitesimally zoom in on this spot right here, I would see that the line is only touching x as a function of t only one time. So I've satisfied Euclid's definition. But clearly, this doesn't look anything like what our tangent looks like, where we're trying to determine the instantaneous speed at a point. The other issue is that in order for me to determine the slope of this tangent that we've drawn here, I have to be able to identify actually 2 points on this curve, right? In order to describe a line, I need a first order line to be clear. I need at least 2 points to be able to fully describe that line under the normal conditions. Well, if I do that, then I essentially have a curve that might look something like this, where now I am not satisfying Euclid's definition, even though this additional line that I've drawn looks like the tangent line that we had drawn before, but now it's touching the curve more than once, right? In my effort to try to define 2 points, for example. And so even though it looks like this, the question becomes, well, is this my tangent, or is this my tangent, or is this my tangent, right? In other words, there could be nearly an infinite number of possibilities that would be the tangent to the curve at this point, but without some means of actually verifying exactly what that tangent is, short of intersecting my curve more than once, I have no means to actually determine what that tangent is, okay? So that then brings up the concept of the limit. The limit is the fundamental concept that allows us to determine the tangent and thereby determine rates of change of physical phenomena that we observe, such as the speed of a vehicle, okay? So let me go ahead and say that the only way to correctly define a tangent is to do so in the context of a limit. Okay? So for this, and we'll talk about what a limit is here in just a moment, or at least you'll see in the example that we do what is meant by a limit. But we'll describe the limit in more detail in later lessons. But at least for now, to visualize what we mean by a limit, it's easiest to visualize with the function y equals x squared, okay? So let's go ahead and draw y equals x squared. And so, of course, that's a parabola around the ordinate. At least it should look like a parabola. If I could draw better, it would look like a nice smooth parabola. But just humor me and suppose that this is, in fact, a parabola. And let's suppose that we want to determine the rate of change oops, that's not working out for me. Just 1 minute. Okay, let's suppose that we want to determine the rate of change at this point here, which we're going to identify as point P. And we're going to say that point P is at 1, 1 on the coordinate plane. Now, of course, I think if you actually look at the number of divisions that I have in my grid paper here, you'll see that it's not precisely 1, 1, or at least the y and the x scales are not perfectly to scale. But again, just if you could humor me for a moment and take point P to be at 1, 1 on the coordinate grid. Okay, so we essentially have determined that what we want to do in order for us to determine the rate of change of this function, right, this phenomena that's described by x squared, right? So there's some phenomena which we would call y, right? Maybe it's the speed of the vehicle, or maybe it's the rate at which a medicine is absorbed into a body, or maybe it's the rate at which the sugars are produced during a photosynthesis process for a biological plant, right? Or maybe it's the way that the torsion within a metal bar changes as it undergoes twisting, right? You pick any infinite number of possible natural phenomena that we can describe using calculus, and that's what y would be, okay? That's your dependent variable. And according to this expression, that dependent variable changes according to x squared, right? That's the model by which that phenomena changes, whatever it might be, okay? And so at a particular moment in time, we want to determine that rate of change of that dependent variable as a function of its independent variable, x, okay? And so as we've already established, what that means is it means, well, we need to determine the slope of this curve, right, based on whatever the tangent is to that point. But we have to determine what that tangent is. So we're trying to determine the slope of a curve using only one point, right, which we ordinarily cannot do. So what do we do instead? Well, what we do is we say, okay, let's just, at least to get the conversation started, let's approximate the slope of this tangent line, m sub t, by determining the slope of a secant, right, or a slice of a line that goes between points P and what we'll call Q, okay? And so we have the secant, which is line PQ, right? And we're going to just for a moment suppose that this approximates the tangent at P, okay? Okay, so now I've got 2 points on the curve. I have my first point, which is 1, 1, and then I have point Q, which I'm just going to arbitrarily, well, it's not arbitrary, but I'm just going to simply say that that's at some value x. And of course, if it's at some value x, then it's going to be at some value y, which is given by the function itself. And so my x value is x, my y value in this case is x squared, okay? Okay, so now since I'm saying that this secant PQ is an approximation to the tangent at P, I can go ahead and determine the slope of the secant PQ, okay? And again, we're going to say that the slope of PQ is going to be some rough approximation to the tangent at P. So the slope of PQ is, of course, the change in y divided by the change in x. So the change in y is obviously y2 minus y1, and this is divided by x2 minus x1. So for this arbitrary point Q that I've picked, y2 is simply x squared, right? That's the y value at point Q minus the y value at point P, which is just 1. And then I divide that by my change in x. So x2 is point Q. So the value of x2 is just x, minus x1, which is the x value at point P, which is 1. Remember that point P is at 1, comma 1. And so the denominator, the change in x, is just x minus 1. Okay? So now I can calculate the slope of PQ for any value of x. So let's suppose x is equal to 2, right? So we're 1 unit away from the point at which we're trying to determine the tangent, the slope of the tangent, okay? So at x equals 2, well, now I have a value, so I can determine MPQ, the slope of line PQ, right? So I plug my 2 into my equation, right? So this ends up being 2 squared minus 1 divided by 2 minus 1. And so this, of course, is 4 minus 1 divided by 2 minus 1, which is obviously just 3. Okay? So the slope, MPQ, for when Q is equal to 2, comma 4, right? So when x is equal to 2, that places Q at the point 2, comma 4. So then the slope between the slope of the secant, PQ, the line between point P and point Q, is then equal to 3. Okay? Okay, well, let's now suppose that, because this is a line, right, we can run this line as long as we can put this point Q anywhere along the function that we want, right? So rather than perhaps have the function at rather than have point Q at x equals 2, let's suppose point Q is at x equals 0, right? So let's suppose now we calculate the slope of the secant PQ for when point Q is at x equals 0, right? So let's instead suppose x equals 0, okay? So now that means that point Q is down here at x equals 0, and we still have the secant that's between Q and P. P hasn't changed. P, remember, that's our point of interest, so P hasn't changed. So then the slope, MPQ, is now equal to 0 squared, or just 0, minus 1, divided by x, which is equal to 0, minus 1. So we get negative 1 over negative 1, which of course is just equal to 1. Okay? So if I place Q at x equals 2, then the slope of the secant between P and Q is 3. If instead I place point Q at x equals 0 and calculate the slope of the secant between point Q and point P, then the slope of that secant is 1. Okay? So how is this helping me, right? I'm trying to determine the slope of the tangent at point P, and if I look at 1 unit to the right of P, where x equals 2, and then I look at the slope of the secant where point Q is to the left of P by 1 unit, and I get a different slope. This doesn't seem to be helping me if the slope of the secant is meant to approximate the tangent at P, right? Do I say that the slope of the tangent at P is 3, or do I say it's 1? Okay? So before we answer that question, let's try to make the distance away from P smaller. Rather than move away from P by 1 unit, let's move away by half a unit, okay? So let's instead fix point Q at x equals 1.5, okay? So now we're going to have Q be somewhere between P and the original point of Q, right, where x was equal to 2. So we now have x equal to 1.5. So when we do that, the slope of our secant between P and the new location of Q at x equals 1.5 is again our change in y with respect to x. So this would be 1.5 squared minus 1 divided by 1.5 minus 1. And that gives us a value of 2.5, okay? So let's then say, all right, well, what happens if I go to the left of P by half a unit, right? So that would be an x value of 0.5. So I've now moved Q to 0.5. So I'm somewhere here, okay, with my point Q. And I can calculate my slope of the secant between P and my new location of Q. And this becomes 0.5 squared minus 1 divided by 0.5 minus 1. And I now get a value of 1.5. And so what we see is, again, different values for the slope of that secant. But notice that the slope at when Q is at 1.5, an x value of 1.5, the slope is 2.5, whereas before when Q was at an x value of 2, the slope was 3. And then on the left-hand side, when Q was at 0.5, an x value of 0.5, the slope of the secant is 1.5, but when it was at x equals 0, the slope was 1. So both slopes changed, and they changed in such a way that regardless of, when we look at the value of Q, the location of Q either to the right of P or to the left of P, the slopes of those secants are approaching each other, right? In other words, we went from 3 to 2.5, we went from 1 to 1.5. The slope of the secant when Q is to the right of P decreased, but the slope of the secant when Q is to the left of P increased. And they're starting to approach each other, okay? So that's good, right? That means that we're actually potentially converging on a value of what the slope of the tangent at P would be if we can make the length of this secant, PQ, as short as possible, as small as possible, and try to get that secant to as closely match the tangent as we possibly can. So let's go ahead then and change our x values more, where again we try to make x such that the point Q is closer and closer to P, looking both to the right of P as well as to the left of P, okay? And so by doing so, we can create a table. And so we can have a table of x values that are to the right of P, right? So you'll notice that I used a plus sign there. That means to the right of P, where Q is to the right of P. And we can calculate our slopes of the secant PQ for those various values of x that are to the right of P. And then we can also create a table where x is to the left of P. Notice I used a minus sign there. And so this would be x values that are to the left of P. And I can correspondingly calculate the slope of the secant PQ when Q is at an x value to the left of P. Okay, so we've already done two values of x that are to the right of P. So we did 2 and 1.5. And of course, we calculated the slope of the secant when Q is at x equals 2. That was 3. And we also did it at 1.5. That was 2.5. But we can add more values of x that are to the right of P. And so we can look at 1.1, for example, and we can look at 1.01, And we can look at 1.001, okay? And when we locate Q at these three additional values of x, what we calculate the slopes to be are as follows. The slope when Q is at 1.1 is 2.1. And when Q is at x equals 1.01, the slope of the secant is 2.01. And when Q is at the point x equals 1.001, the slope is 2.001. Okay? And you can see what's happening, right? The slopes of that secant between points P and Q are starting to converge to a value, okay? Well, when we do limit analysis, and again, we'll go more into this as we learn more about limits, but when we do limit analysis, we can't restrict ourselves to only looking at one side of the point of interest. We have to look at both sides of the point of interest. And so we have to look at how things change as we approach point P from the left side of P. And so, again, we've already done two of these. We looked at when Q is at x equals 0, and we looked at when Q is at x equals 0.5. And so the slope of the secant between Q and P when Q is at x equals 0 is 1. And the slope of the secant between P and Q when Q is at x equals 0.5 is 1.5, right? That's what we calculated above. But we can look at additional values of x that are to the left of P. We can look at x equals 0.9, 0.99, and 0.999, okay? And when we calculate the slopes of the secant between P and Q, when Q is at these three additional values of x to the left of P, we get a slope of 1.9, 1.99, and 1.999. And again, what you see is that this slope is approaching a value. And what further you see is that when we approach point P from either the right side or the left side, the slope of the secant of that line between P and Q is converging to the same value, right? It's converging the value of MPQ as we approach P from either side of P is converging to the same value. And it's fairly clear that the value that it's converging to seems to be 2. Okay? So, this is where calculus gets very interesting, right? Because we can't, at this moment, we can't definitively say that the slope is 2 because we're doing this in discrete values, right? And we could continue this until we add another value of x on the right side of P and another value of x on the left side of P. And we will just do this ad nauseum to infinity, right? Where we basically add an infinite number of values to the right of the decimal point on the right-hand side and an infinite number of values to x on the left-hand side, okay? And all we're going to do is simply add more and more digits, right, that are more or less confirming that you're getting really, really, really close to the value of 2, okay? And so we're going to explore that idea further, and that's sort of the fundamental basis of calculus and the basic idea of how limit is the foundational fundamental concept of us being able to determine rates of change, okay? But for the purpose of this example, we can more or less say that the slope of PQ seems to be approaching 2, right? as Q approaches P, which would be to say that the slope of our function at x equals P is probably equal to 2, okay? And I'm going to put in parentheses here probably because, again, we've not really actually solidified this with any laws of calculus to definitively say that this is indeed what's happening. And certainly I don't mean to spoil anything, spoiler alert, but this is essentially what we discover as being the laws of the limit in order to establish this foundational principle for calculus, okay? So the way that we would write this generally, okay, is we would say that, okay, the limit as Q approaches P of the slope of the secant PQ is equal to the slope of our function at point P, okay? And since we had our x value of interest was 1, right? So remember, this was our point of interest. So since the x value is equal to 1, we can further say that the limit as x approaches 1 of this function x squared minus 1 divided by x minus 1, right? This is this x squared minus 1 divided by x minus 1, that's equal to MPQ, okay? That value is converging to 2. And so we would more or less be able to say that the slope of our function at x equals 1 is equal to 2, okay? Okay, so later on, what we're going to show is all these other things in the realm of calculus that you've probably heard before, like derivative and integral. These are all defined in the context of the limit, right? And we essentially will be taking the limit as it approaches infinitesimally to the point of interest, or we take an infinitesimally small slice of something to determine the integral, for example. But we'll obviously go through all of this in more detail as we develop more lessons, okay? But it's important to understand this concept of the limit, and it's the limit that allows us to focus in exactly on this point right here and say, okay, I can indeed determine the slope of the tangent at point P by taking the limit of the secant as the second point of that secant approaches the point of interest, which would be P. And so to relate that back to our earlier discussion about determining the instantaneous speed of the vehicle at this point, we do essentially the same thing, right? We basically say this is our point P, and we're going to determine or define some point Q, and we're going to determine the limit of the slope of the secant between P and Q as Q approaches P. And as we allow Q to infinitesimally approach P, that will allow us to determine the instantaneous speed of the vehicle at point P. Okay? All right. Hope you enjoyed this lesson, and we'll look forward to lesson number 2.